Okay, so we're continuing on with section 4.2, and we should be now finding lower and upper sums for a region using that method we just talked about with the lower sum and the upper sum. So we need to find, according to the last page here, we have to find, if it doesn't tell us how many subintervals we're using. So on the last example, we had very concrete, we had 5 subintervals. But if we don't know how many, it's n, then we're going to have to use delta x, which is b minus a over n. So that's where we're going to start. Delta x is b minus a over n, which is 2 over n. And then we're going to have two different sums. We're going to have the left sum and the right sum. So for the left, we'll have lowercase m sub I, which we take the first term of our interval, 0, and we add, remember the I minus 1s we could get to the left, which is 2 times I minus 1 all over n. And the right, which we'll say is our capital M, take the first term of our interval plus I, 2 over n. So this is 2I over n for what we're plugging into our function. So still on the left side over here, we'll have our sum lowercase s, which is from I equals 1 to n, plugging in our f sub I times our delta x. I'm going to go through and finish all the work, or I'll just at least write down the rule for right, but then I'm going to go through and do all the work for the left and then all the work for the right. So for this capital S sum from 1 to n, f of 2I over n times 2 over n. Okay, so now coming back over to the left side, sorry, to plug this into the function, which was 2x squared, or was it just, hold on, just x squared, okay? So I equals 1 to n. We take the m sub I and square it. Oops, that should be a bracket. Times our width, which is just 2 over n, because I don't know how many intervals I'm using. Okay, this would have to be FOILed out, the I minus 1 squared. And there's going to be an 8 when we square the 2 and then multiply it by the other 2, and then the n squared and the n. We're going to have 8 over n cubed outside, and then 8I squared minus I plus 2I plus 1. So remember, right now we're going to bring out that 8 over n cubed because the sum substitutions are all involving just the I. Oh my goodness, I'm getting my I's and my 1's. It's crazy. All confused. There we go. So now we're going to do our 3 different substitutions, one for the I squared, one for the 2I, and one for the I. So I'll split this up so we can see what we're doing. I squared, 2I. I'm actually going to bring the 2 out as well to be with the 8 here to make 16. Since our substitution is really just for I. There we go. And then we'll do our 3 substitutions for the I squared, the I, and the 1. I squared turns into 2n cubed plus 3n squared plus n all over 6. I turns into n squared plus n over 2. And 1 turns into n. So through a lot of algebra, substitution, things like that, this is going to simplify to 8/3 minus 4 over n plus 4 over 3n squared. Okay, now let's go do the right sum. Okay, so now I'm going to plug the 2i over n into the function. So 2i over n, whole thing being squared, times 2 over n. So squaring that, it's going to be 4i squared over n squared times 2 over n. So again, we're going to pull out the 8 and n cubed up front. And I'm just taking the sum of I squared here. Well, that's quite a bit easier, considering here I had 3 terms to deal with, and now we just have 1 term to deal with. The substitution for I squared is the 2n cubed plus 3n squared plus n all over 6. And then I substitute that, or simplify, not really substitute, but simplify that in a couple steps, and I'm at 8/3 plus 4 over n plus 4 over 3n squared for my upper. So look how similar these are. The only difference, even though we did so much more work over on this left side, the only difference is that this is minus 4 over n as opposed to plus 4 over n. It seems like if we could pick, I would choose to do the right every single time. And it turns out when we look at the next page here, when we take the n, the number of n subintervals, and we set that to infinity, because really we want that area to be as exact as possible. So we want as many rectangles as we can cram into that area as possible, as small as possible. So if we have potentially infinite intervals, infinite rectangles in there, then we're getting exact area. So if I take the limit of our answer as n approaches infinity, let's go back and do that now. We have 2 answers. If I take the limit of both of these boxed answers as n approaches infinity, both answers are going to give me 8/3 because those n's on the bottom of both of those are going to cancel. Basically 4 over infinity, which is 0 both times. Those are going to cancel out. So really, we get 8/3 either way. So now that we know we can do that, we should just stick with the easier side every time. So now our new formula that we're going to be dealing with is just the capital M, just the easy side. So all we need here, instead of doing the minimum and the maximum, we're just going to treat CI as our function every time. This is it. Take the first term of our subinterval plus I times delta x, and delta x is our b minus a over n. So remember that this is our right. And it's much, much easier. If we're asked from here to do the left, you should still do it, but the CI would be a plus I minus 1 delta x, because that's going to get you the left instead of the right. Okay, just a couple more examples with that. And we're just going to do the right now that we know if we take the limit as n approaches infinity to find the area, we're going to get the same area either way. So why not use the easier one? Here we have our interval is from 0 to 1. So delta x is 1 over n with n subintervals. So then our CI is 0 plus I times delta x over I over n. So we're going to do our new addition to the formula here is this limit as n approaches infinity on the outside, which makes it so that we can always use the easier version and still get the same answer. X cubed, so CI I'll do the basic one first so you see what I'm doing. F of CI delta X. So now I plug that CI into my function x cubed, I over n cubed times delta x, 1 over n. Anything that's not an I or a constant gets brought out to the front. So we're taking the limit as n approaches infinity of 1 over n to the 4th of I cubed. Now we do our summation substitution for I cubed, which is n to the 4th plus 2n cubed plus n squared all over 4. And since we're doing n approaching infinity, I really just want to compare, make sure that our powers are the same on the top and the bottom. And then I'm really just going to be looking at the highest power term here on the top versus the highest power term on the bottom. And the coefficients are going to be my answer. So 1/4. It's kind of a little shortcut, so you don't have to do every single, break it up into every single step. Okay, one more example. So we're from 1 to 2. Our delta x is 1 over n, and our CI is 1 plus I times delta x. First step is plugging the CI into the function. So this time our function is 4 minus x squared, and then multiply the whole thing by delta x. So we're going to have some foiling and rearranging to do. If I just do my one foiling step without doing anything else, combining the 4 with the 1 when I subtract that, then I'm going to have 3 minus 2i over n minus I squared over n squared. That's still being multiplied by 1 over n. At this point, then, I would split it up into the 3 separate summations. The first summation is if I throw the 1 over n on the outside, here, let's just do this, 1 over n from the delta x, then all I have left is 3. On the next one, I would have a 2 over n squared on the outside. And all I have left in here is I, and the last one would be 1 over n cubed, where all I have left is I squared. And then I can do those substitutions. Hopefully they fit. 1 over n times 3n minus 2 over n squared times n squared plus n over 2 and 1 over n cubed times 2n cubed plus 3n squared plus n all over 6. So there's a lot of simplifying here that can be done. Or we can just look at, like I mentioned before, the biggest power. So here the n's are going to cancel, and this is just going to be 3 when I simplify. Second term, if I have n squared on top and n squared on bottom, then I have minus 2 over 2. And the last one, my top is going to be 2 and the bottom is going to be 6. So it's 1/3. So that saves us quite a bit of simplifying time if you do that trick. And the answer here is 5/3. There we have it, section 4.2, second half. on summations.